Hello, in this video we're going to be looking at forces for linked objects, where you have two objects connected by a string and they're sharing the same acceleration. It's a common set of problems in early physics. So, like many other physics problems regarding forces, a good starting point is just to draw a picture of what's going on, and in that picture you want to identify the direction of motion for each object and the forces for each object, and draw a coordinate system as well for each object. If they're just on flat level surfaces, you're fine using the standard x is horizontal, y is vertical, but if an object's on an incline, you'll have to rotate things. Once you've drawn those forces and the coordinates, you'll insert those forces into F equals ma equations for each object, and you'll keep each object separate for a while and do whatever manipulations you can, and then at the very end you'll combine the end equations for each object to get rid of the tension, because you normally don't know the value for the tension ahead of time. In these sorts of problems, there are a number of assumptions that you can normally make, especially in early physics. Starting out, pulleys can be treated as massless. When you have massless pulleys, you don't need to worry about the torque for the pulley itself. You can just worry about the two moving objects. And another common set of assumptions that you can make are that the strings or ropes are massless and stretchable. And so this has a number of important implications. If the string doesn't have mass, you can ignore any force equations for the string itself, and you can ignore any catenary or drooping of the string. And if it's unstretchable as well, the tension is going to have the same magnitude on either side of the string, and the accelerations are going to be the same, are going to have the same magnitude on either end of the string or rope as well. And this will allow us to say the acceleration motion for block A has to have the same magnitude as the motion and acceleration for block B. So let's look at a common example where you have one object on a table and another object hanging off to the side. So what we're going to do first is identify the direction of motions, the forces, and a coordinate system for each object. This was what it will look like. Let's start with block B, the one that's hanging down here, and as long as you're on Earth, you're going to have gravity acting downwards, and tension points to the other end of the string, you can think about it, or away from the object. So gravity's acting down, tension's going up, and assuming that there's nothing else acting on the system, like no one pushing or pulling it, you can safely say that the direction of motion for the system is where block B is going down. And if it's just hanging in air, there's probably no X or horizontal forces acting on it. For the block on the table, assuming that, again, that there's no one pulling on this thing, the hanging mass is going to be dragging the one on the table across. So we'll say the motion for this is to the right in the same direction as the tension of the string. And if it's on a rough surface, maybe there's some friction opposing that motion. And as long as you're on Earth, there's going to be gravity acting on it. So block A is being pressed onto the table is going to be pushing back with a normal force. And since everything's perfectly horizontal or vertical, we're safe using the horizontal and vertical coordinate system. So with that picture, let's treat each object individually and look at the forces acting on them and put them into a set of equations. So let's start with block B, the hanging mass, because there's less going on. So there's no forces acting on it in the horizontal, so nothing's happening there. All the forces are in the y direction. we have tension going up and gravity going down, and we've identified the direction of motion as downward, and so we have to assign a negative value to its y acceleration. This is very important because we're linking the magnitude of the acceleration for block B to block A. And so in order for the magnitudes of the accelerations to be consistent, we have to be mindful of the sign. So since our acceleration is downward, it's going to be in the minus y direction. We need to attach that negative sign to the acceleration. For block A, we have a little bit more going on since we have both horizontal and vertical forces. In the horizontal direction, we have tension going one way, and if it's being pulled to the right, friction is going to be acting on it going to the left. And it's accelerating to the right, so it's going to have a positive x acceleration. Again, we're linking the acceleration for A to the acceleration for B. In the y direction, we have gravity going downwards and the normal force going upwards. And as long as this thing is staying on the table, they have to cancel each other out. So this means the normal force on A has to equal the force of gravity on A. For early physics, we can directly relate the force of friction to the normal force through a coefficient of friction. And so by looking at the forces in the y direction, we can get the normal force, and from that normal force, you can determine the force of friction. And if we substitute that expression for the force of friction into our x direction equation, we end up with this end equation for block A, where the tension minus the force of friction on it, which is coefficient of kinetic friction times its mass times g, is equal to its mass times its acceleration. And that's as far as we can go with block A, because we probably don't know the acceleration and we don't know a value for the tension ahead of time. So it's at this moment that we need to combine our end equations for block A and block B. So let's look at that. So for block B, we just had the one equation for it, for the vertical motion, where the tension's going up, gravity acting on it is going down, and it has a negative acceleration. Then for A, we had the equation where the tension minus the force of friction is equal to its acceleration, and is being accelerated to the right. If we rearrange this, this means the tension is equal to the mass of A times its acceleration plus the coefficient of kinetic friction times its mass times g. So we have an expression for tension in one equation. Let's substitute it in for the tension in the second equation. So what we'll do is we'll put in the expression for the tension that we get from looking at the forces into block A, and we'll put that into our equation for block B. When we do so, we have our tension, which is mass of A times its acceleration plus the coefficient of kinetic friction times the mass of A times g, that was our tension, minus the force of gravity on B, and Bg, is equal to the mass of B times its acceleration. And again, we assign a negative value here because it's moving in the minus y direction. And we know all these terms except for the acceleration, so we can rearrange stuff and we'll end up with this expression for the acceleration. Again, the key is you look at each object individually and do the F equals ma equations for each object, go as far as you can, and at the very end you'll have to combine the end equations for each object to get rid of the tension, because you probably don't know the tension ahead of time. Once you do that, you can solve for the accelerations. And you have to be very mindful of the signs for your accelerations, because it has to be consistent across each object. So to repeat, as with any force problem, you want to draw a picture, identify the direction of motion, forces for each object, and the coordinate system for each object, and insert those equations into F equals ma equations for each object. As you do so, you have to be very mindful about keeping the signs consistent for the acceleration, because the acceleration has to have the same magnitude for each object. So if they're moving to the right, it's a positive x acceleration; moving left, negative x acceleration; moving up, positive y acceleration; moving down, negative y acceleration. And you do what you can for those equations for each object, and then combine them at the end of the day to get rid of the tension. And at that point, you should be able to solve for the acceleration.